All right, here we have class 16. We're going to talk about instantaneous center rotation. This is a much better topic than the next one, the acceleration. This is a sort of a break because this is a relatively easy technique to do a velocity analysis. All right, I think I'm going to go back to OneNote again. One of these days, Microsoft will fix their issue with this, with the pen. All right, so the instantaneous center rotation is like this magical point at any particular instantaneous, right? There's going to be this point about which it can appear that this translating and rotating piece is actually only rotating about that fixed point. And so that same general equation that has the velocity at a particular point is equal to the velocity of a reference point plus the velocity, the angular velocity or relative velocity, which is made up of the rotational, is pivoting about that point, and this ICR ends up being equal to 0. Now, this point doesn't necessarily have to fall on the body, and it doesn't have to be not on the body. It can be somewhere off in space, or it can land somewhere on the body. So once we find this instantaneous center of rotation, we can find velocities all over the place, which makes it very convenient. So as soon as you find the location, and there's a graphical way to find this, and it relies on the fact that the radius of the instantaneous center of rotation, which I will often write like this, I'll put this little bracket to the side and say, this is my the radius of A with respect to ICR. And we know that it's perpendicular to the velocity. So that's the trait that we're going to use to identify this instantaneous center of rotation. So just make up a couple points right here. If we happen to know where the ICR is, right? So if we have the ICR and we can draw a line from it to the point that we care about, and we know that the velocity is going to be perpendicular. Try to draw that a little better. Try to make it actually perpendicular there. That's the velocity of A. I just mix around colors here. We know that's perpendicular right here. And then as soon as we have this omega, the rotation about that thing, we can find that we could find the velocity. But I think I wrote something else that says, okay, so these are the general cases. I should have read this. When the velocity of a point VA is known and the rotation is known, then we can find this RA with respect to ICR. And we don't have to write it as a vector. We're just looking, we know the positions just because of the nature of the thing. So we could just find it, hey, want to know what the magnitude is of this guy right here. All we have to do is say VA divided by omega AB. I guess that's omega AB. Right, because this is the rewriting of this, so we can always just go to this equation right here. I should have really started. I'm not going to restart it. I'll just keep going with this. Okay, now we'll go to this next case right here when we have two velocities and we know both of those velocities. So let me see. So this is like not the same problem right here. This is going to be maybe a different ICR. I guess maybe I kind of drew it the right way, so I'll see here. So like if we know this VA and we know this VB, we can find, we could draw, come on, stop that. The palm is causing this thing to happen. We can draw lines. I'm going to try to make them perpendicular, make them better here. So we draw a line that's perpendicular to VB, and we can draw a line that's perpendicular to VA, and we find where they cross, and that's the ICR, right? And so if we have either one of those things, we're able to find what the omega AB is going to be, the rotation about that thing. We're relying on the fact that these are going to be perpendicular. So that's like a graphical way, but we not only graphical, but we can we could figure out from magnitudes what those are going to be. One special case is when the velocities, when the points are in line with each other, and I guess this makes the points in line with each other. When the velocities are parallel to each other but not equal, the line that's perpendicular is in line with each other. They're both, right here, perpendicular. What we find is the ICR can be found by a triangle right here, or taking the magnitudes, so that, let's see, I will make it so it's like, this is going to be our A with respect to ICR, and this is our B with respect to ICR. And noteworthy that the rotation of the thing is going this way, omega AB. Now, if you had that same situation, but these are equal to each other, VA and VB are parallel and equal, then that perpendicular line, the line that runs perpendicular to both of the velocities, you'll notice that the triangle never forms. So this, by definition, by having those 2 points be parallel and equal to each other, that means that there is no rotation. It's purely translation. Now, just quickly going through a couple points here, or a couple situations. We want to make sure that we draw the lines that are perpendicular to each other to be able to identify that the ICR is right here. And we'll note that means that the rotation right here has to be right here. That's omega AB. You notice that rotation causes this velocity when you have this RA with respect to ICR. And that rotation causes this velocity when you have RB with respect to ICR. Here's just another case right now. One thing that's common to do if you're not thinking too closely on this problem here on the left is sometimes you might pick that point as the ICR, but remember these are the lines that are in line with the velocities, and so don't fall into that trap. It's very easy to do. Make sure that you're drawing lines that are perpendicular to the velocities. Like right here, once again. Lines that are perpendicular, they intersect, and that's the ICR. And you can see that it's rotating in this position. Now remember that rotation doesn't matter that it's about the ICR. That rotation is still true right here, it's still true right here, it's still true right here, it's still true right out here. It's all the same rotational omega. It doesn't matter that we've drawn it about the ICR, but that ICR is effective in figuring out what the rotation of this piece is. And remember, it's still translating and rotating. It's merely that the ICR is an effective way of trying to find the thing. Now, okay, so here's the situation, once again, where we said that the velocities are parallel to each other. So now, in order to find that ICR, we have to use like the magnitudes of the two. So what you could do is, if you knew these velocities right here, you could set up like an equation for a triangle to be able to find these. And Anyway, so that's the ICR, and the thing is rotating that way. Here's a special case where we have a wheel, and that if it's not slipping, that means the ICR is going to be right here, where the velocity has to be 0, right? Because the ground doesn't move, and that wheel has to have the same velocity as the ground, otherwise they're slipping right here at that point. So therefore you have a rotation right here, omega, you can find, and of course we're calling it omega 1 there, so it's the same omega. And one aspect of this, as soon as you find a point, say that you want to find the velocity of that point, all you have to do is use the geometry and find the velocity right here. So this, you just need to find this r, and if we call that a, RA with respect to ICR, or it's really is, if that, say, let's C, sometimes we pick that as C for some reason, it keeps coming up. This would be VA with respect to C, which is ICR. Okay. I think I ask rhetorical questions here. Why does it greatly simplify it? Because once you find the ICR, you can find the velocity anywhere. Why? You can only do this with velocity analysis, or at least the ICR, we're finding this, you can only do it with velocity analysis. But it's not suitable for acceleration analysis. And that's because when we had the velocity in, let's say, tangential coordinates, we had the magnitude times only the tangential unit vector. But with acceleration, if we're going to write that in tangential coordinates, we'd have, we have that tangential magnitude, but we also have a normal component, right? And so what we're really doing with ICR is using this trait right here, which can also be written in other vector note. For any vector, I guess you could write that v is going to be equal to the cross product of the rotation times that r, that reference to whatever center that you happen to have. So if this was a with respect to b, this is also a with respect to b. So we're using the trait that the velocity is equal to the tangent one, and we're taking that perpendicular off of the thing and finding this center of rotation, the same thing what we were doing right there. The center of curvature of the path would be the center when we're talking about tangential coordinates. But we have this extra component right here which messes up and doesn't make the acceleration tangent to and have that perpendicular. Each rigid body has its own ICR, right? But they share the same velocities. When you have multiple linkages, we could see that linkages have can have a shared, or can have we can use the position of the linkages, because the velocities, the relative velocities are going to be the relative velocities are going to be perpendicular, and because to the linkage. And of course, so now with the linkage, the ICR is going to be often on a line that's in line with the center of the linkage. I don't know if I said that correctly in there. So relatively speaking here, we can often find that for linkages, we can extend a line right here to find ICRs. I'm not going to go through these mechanisms too much here and start talking about them. I want to get to the video. I have to make another video as well today, so I got to get moving along. But just to note a note, because it was in there, that 4-bar linkages are a pretty important fundamental when we go into the topic of mechanisms, or when you would, if you're a mechanical engineer, often you care about trying to create some type of device that has mechanical linkages in it. This 4-bar linkage, which is made up often of a crank I'm trying to remember the names of these other pieces. Anyway, they give each of these 4 bars a name. This for the 4th bar, when you look at this thing, is the ground. They're calling that a bar. So you can see that it's has these 1, 2, 3, and then 4 linkages. And there's even a concept that when we have something called like a slider crank, that's what we like to call this. That's really a lot like a piston, right? Like in a car, where you have like a piston and a crank rod and a crankshaft. That can actually be thought of as a special case of a 4-bar linkage, where one of the linkages is like infinite, right here, so that the thing slides back and forth. Because for some pieces, like as you turn them, this thing just slides back and forth. So, and they're very similar. And for these 4 bars appear up in all kinds of different pieces. I won't talk through everything. At least like these guys right here, these are like slider cranks right here that you can see that the motion of the thing causes these to go up and down right here. But you also have, like, maybe if you had like this device right here, here's your 4 bar right here. And in this case, here's your 4 bar right here. Of course, here's the ground right here. Or here's your 4 bar. Let's see if I do this one right here. Here's 4 bar, boom, 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 and then boom, there's your 4 bar. It's interesting kind of stuff that you can create all these. Also interesting that you can use this, if you put a little pointer on one of the bars, on your 4 bar right here, you can start to generate motions, particular motions, and the proportions of these bars can be used to have a specific type of if you want to make a device that for whatever reason makes this funny little triple loop thing, you can. Another one that you could think of is like I like to think of is like if you had some device, if you like rotate this thing around, that you had a piece that you wanted to have like a bucket of something, right? You had the bucket and you needed to make a dipping motion, and then you needed to pick it up and come back up. And you needed to do that repeatedly. You could get the proportions of this thing so that the travel of the path of the thing went down, picked up, and then came back at a different path, and then it circled and it did the same thing. So you could make this scoop. That kind of idea of trying to make something that to have a certain motion you wanted to capture, and you could figure that out. And then also there's some famous mechanisms, proportions of mechanisms that are able to make, at least in one part of their path, make a straight line. And so you could see like maybe this guy right here, he is the same kind of idea. And the straight line, being able to make a straight line often is something that's convenient for certain types of mechanicals. One of them, this is the Watt straight linkage. And that's James Watt, same steam engine guy, made this little device here. He was reportedly was very proud of it, that he was able to make this, came up with these proportions, and that helped as part of the mechanism that controlled the valves on his reciprocating steam engine. So that's a little interesting piece of history right there. So we have a problem right here, and I decided to change it so that L was equal to 4 meters, because otherwise it's just doing the problem in terms of L, and I found that to be boring. So that means that this guy right here is 4 meters, and that this guy right here is 4 meters, because they say that this is length L, and that this guy, he's L over 2, so he's going to be 2 meters. Those are supposed to be meters. It looks like a W. And see, okay, so this is 135 degrees right here, this guy. And this guy is 45 degrees. And he is 135 degrees. So first, note that when we march through this piece, I'll start out with this linkage right here. And when we have this, we have the ICR is the same thing as the pivot point right here. So we don't really need to find an ICR. It's already found for us. But what we can have is the same general idea, is that we don't need to do vectors. We just go to magnitudes and say the velocity of A is just going to be omega AC times R, A with respect to C. Of course, this is the same thing as A with respect to C. VA is VA with respect to C, which is going to be 10, because they told us that this thing, let's say, is going this direction. I should have drawn it on there. Go red, right here. That it's positive, so this must be counterclockwise. So that's omega. They call it CA. I can't stop myself from calling it AC. I like to put them in alphabetical order. So that's 10 radians per second, and that distance is 4. So that's easy enough, 40 meters per second. Now we can go to the, I'll go to this other linkage. I go for BD right here. So we're going to use the fact that the velocities are going to be perpendicular here. And we don't necessarily know which direction BD is going to rotate. We could probably think it through, but I'm going to put a little question marks over here. We don't know, is it going to the left? Is it going to the right? Which way does it rotate? We don't know, but we can use that line as part of our geometry when we go to the next link, when we go to AB. I'll draw it with a little curvature right here. Right? We can use the fact that we know the velocity at A has to be, right, this one. We already know what that velocity is going to be. And we know that, what are you doing right there? Why would you do that? We know that the velocity here has to be in line with this right here, right? So that's the line that's parallel to this line right here. So if we drew perpendicular lines, we have to be careful when we have a problem like this, that the line that I just drew is not the line that's perpendicular. We have to draw, like in this case, I'm trying to draw like separate colors. Let's see, I haven't used purple here. This is the line that's perpendicular to both of those, right? So that's where the ICR is going to be. And from the geometry that we had up above, let's see, I'm not being consistent with my colors. We know that this is 4 right here. And we know that this is going to be 45 degrees right here. So we can find what the radius of A with respect to ICR. So it's going to be this guy right here. We know that this is, we're looking at this, we could figure out that that has to be 45, so that has to be 90 degrees. So we know that the hypotenuse of this triangle is the 4. So if we want to get one of the legs, and I guess I put the 40, if I use that 45, it's going to be cosine of 45. So that's 2.828 meters. All right, so I already wrote the answer. What am I doing? All right. So now I can find, I can write out that the velocity of A is equal to omega AB R, A with respect to ICR. So now I found omega AB. It's going to be VA with respect to R, A, ICR. What did I say that? I just said no. VA divided by R, A with respect to RCR. All right, so that's just going to be 40 divided by 2.828, or 14.14 radians per second. Yeah, need to use my space better. And I think that's what they're asking. Use the instantaneous center rotation to find the angular velocity of the curved link. Okay, so that's what we found. AB is equal to 14.1 radians per second. And if they were going to ask for a vector, they weren't clear, so let's just assume it was a vector. We could either write this as, oh, by the way, I didn't write in the direction. Okay, so once we find that ICR, that helps us figure out what direction that's going to be. So that's the omega. So we find out that if we're going to do the answer completely, we need a direction in there. Alternatively, we could have written as a vector 14.1 k, right? And that, negative right there, yep, per second. And that would have been an answer that was correct, because we had that K in there and negative. That establishes, hey, we know that counterclockwise is the convention for positive and negative. One last thing in here, I could have drawn to answer this question. Hey, what direction does this linkage BD go? We didn't know, but once we found that ICR, we knew that it had to rotate this direction. Therefore, this had to be in, that was the answer. It had to be in that direction. So it had to rotate about there. And that might not have been 100% clear. You will often find that in a linkage that you're having a rotation. If this guy rotates this way, that guy rotates this way, and then this guy rotates that way. That's not always true. I'm pretty sure I can say that. That's not always true. You could have it like this, flipped right there. You know, I wanted to think about that a little bit more. I might try that out. Anyway, whether it's true all the time or not, you'll often find that to be the case. If it's true all the time, then you will. Not only often, but always. All right. Here's another example right here. Not too long. Are we going? Okay. And so we have a piece here. This is really sort of, I guess this is a 4-bar, but it has like some constraint where C has to be above A. So you might almost think of this as being like a slider thing going right here. Like this is a slider crank, and they're just two slider cranks that are mirrored to each other because they have to have the same motion. And if you didn't prescribe that motion, this thing would not be a fully defined thing. It would have more than 1 degree of freedom, but because it's constrained to move C above A, we have a mechanism that's effective here. Okay, so I can just pick out, let's say, all the linkage. We want to determine what BC is. So I'm just going to draw a linkage BC over to the side. Try to make a good sketch if I can. I know what VC is, boom, right here, and VC. So I'm going to have to be careful with my geometry. They tell us that this is 34 degrees right here, right? So this right here has to be 56 degrees right here, right? If I were to draw a line right in there. And okay, so I had to play around with a bunch of angles in here. Now I know that any velocity that I have has to be perpendicular to the line that's if it's pivoting about A right here, this linkage AB. So it has to be perpendicular right there. Okay, so I'll draw the line that this has to work on. That's it. That velocity at B has to be in that on that line. I try not to say in direction because we haven't established the direction, but whether it's going to go up and to the left or down and to the right. But it's definitely going to be on that line. So I guess I'll use blue as my perpendiculars here. There's a perpendicular line to that velocity at B, and then we have a perpendicular line to our velocity at C. So that's what the ICR is going to be. Now the challenge is going to be able to find what the physical position is of this piece. One of the things that we can do is use the angles that we know of and establish them, and then use our law of sines. So if we're careful with our drawing here, it helps us to establish what all of the angles are going to be. This line right here, I think it's logical. I think it becomes obvious. Let me see how I can say this. I know that, right, I don't want to overcomplicate. There's probably a bunch of different ways to say this without making this complicated, but sometimes my muddled mind makes these things complicated. I want to say that I know that this angle, come on, stop that this angle right here is 34. because that angle's 34. I think I can say that because, let's see. Yeah, because it's drawn right here. Okay, yeah, duh. That is 34 degrees, no. And then this was for the 56. We've already established that. Okay. And because these things are perpendicular right here, right? Because this line right here, this line and this line are perpendicular. This has to be 34 degrees as well. What was my point? I'm trying to remember. And then I also say, okay, well, this has to be 56 degrees. And if I know that, okay, well, then let's see, where am I going with this? Yeah. And that line, what I really want to try to find is what, let's see, I'm running out of colors here. I have used blue, purple, and green and red. All right. Maybe I'll come up here, use orange. There you go. I really want to find this angle right here as part of that. So do whatever it takes to be able to find that angle. And I'm losing my mind right now. Oh, you know what I think I did? I said that if this is 56, then this has to be 56. That's what it is, right? Do you agree with that? I hope so, because it's true. And if that's 56, we also know that this right here, do I have to say that? Can we say that? We say that this piece right here, that this is 34 right here. That one is 34. I think I have to go back to this guy right here. That this, yeah, that this has to be 56 and this has to be 56 because they're symmetric right there, because these are the same lengths right here. Okay, so if this is 56 right here and this is 56, then I can take 180 minus 2 times 56. 56, not 50. And that ends up being 68. Boy, this is really embarrassing. But go ahead. Think I'm an idiot. I don't care. So let me double check that I get the right thing. It's 56 2 times minus 68 degrees. Okay, I knew that was the answer, but looking at what I've written right here. All right. So I've really muddled up this drawing right here, but hopefully, like, maybe I'll draw it over to the side that you can see that I have a triangle right here where I know this is going to be 68 degrees, and I know that this is 56 degrees. So I want to get this position right there. I want to know this RC with respect to ICR because I have this VC, right? So if I take the law of sines, that means that RC over ICR divided by the sine of 68 degrees is going to be equal to my VC. No, that's not true. Let's see. It's going to be equal to this length right here, which I'm given as 1.2 feet. So it's 1.2 divided by the angle that's opposite to it, which is sine, or the sine of the angle, sine of 56. We do that, get RC with respect to ICR of equal to 1.342 feet. So now we're able to say that because we know that the VC is equal to omega BC times RC with respect to ICR, we're able to get omega BC equal to VC over RC with respect to ICR, which is going to be our, where to go, 0.05 divided by our 1.342, which means 0.03726 radians per second. So we can write that thing down however we want to write the thing. I prefer to put an arrow, 0.0373 radians per second. So that's really, it demonstrates some of the challenge is to find that geometry. And is this my last one, or did I have one more than that? I think I decided in class to show this one, to not show this one. Okay, well this one I think also was boring without having any dimensions. So I said that L was equal to 2 meters. And think theta I decided was 30 degrees, and V was equal to 5 meters per second, just to give it some direction. Now they tell us that V right here, right, so that's the same thing as being VA. They gave us that it's to moving to the right, so I could say that right there as a vector on VA. So what I do for this is I just draw the linkage AB, and I know that VA is this direction here, VA. And if I draw this other linkage to the side, this linkage BC, I know that his velocity has to be either up or down, but it's going to be in the vertical direction, constrained to the vertical direction. So I can transfer him over to here, and now I know that if I draw the perpendiculars to both of those velocities, I can find my ICR. And if I know my ICR is there, I know it has to rotate omega AB in that direction. And if the omega OB is in that direction, I know, and I should probably get rid of my guy right here. If I know that omega AB, I know that my velocity at B has to be in that direction. So I can say if I have, I can find these two positions for my ICR, this ICR and this ICR. I go A with respect to ICR is going to be that linkage length, which is 4L. So that makes this thing 8, right? Did I decide it was 8? I write that in place. Yeah, 8. And then this distance right here, this is 2L, so that's 4. So here for my RA with respect to ICR, this is going to be 8 times the cosine or sine, yeah. For the A, that, okay, yeah, because that means this angle right there is also 30 degrees. So it's going to be the sine of 30 degrees. So that makes that 4. And then RB with respect to ICR, it's going to be 8 times my cosine of 30 degrees, which is 6.928 meters. And so now I can write for the velocity of A right here. Velocity of A is equal to omega AB RA with respect to ICR, and rewriting omega AB VA R A with respect to ICR 5. That's the what I decided VA was going to be 5 divided by 4, or 1.250 radians per second is what that omega AB is going to be. And now I can find what the velocity of B is going to be. Another velocity of B. Velocity of B is going to be equal to omega BC times RB with respect to C. No, it's, sorry, excuse me. I need to write B with respect to ICR. So that just becomes that 1.25 times R 6.928 or 8.660 meters per second. And we know that it's going to go upwards right here. Shown in both places. That's VB on that linkage. So lastly, if we want to, we know that that omega BC is going to be in that direction, and we can write that the VB here is going to be omega BC times R, and then I'll just say that that's R. They said C with respect to B, as I like to go on. Well, it doesn't really matter here. It would matter if there were vectors, what order in which you put the thing here. So you said omega BC is going to be velocity of B divided by that R B with respect to C. So it comes out 8.660 divided by 4, which ends up being omega BC, let's make it a vector here, 2.165 radians per second, and it's clockwise. Okay. I think I did this other one in class right here, so I won't belabor the thing. This one, once again, you got to be careful with your angles. I think I should have drawn that a little bit further down. Or even write, make careful sketches, is what I wrote in the thing. And I'm probably not making a careful enough sketch. And my VA goes this way right here. My VB needs to be in that direction, so there you go. So you have to be careful with what angles that you use onto the thing. And then I draw my perpendicular lines here. This is perpendicular. That's supposed to be perpendicular. Here's your ICR. You figure out that this is going to be 45. You figure out from just the geometry of the thing, let's go red, that this has to be 75 degrees. You might have to put some thought process into that, I think. I won't do the little struggle thing. It just makes me look like a moron trying to figure out. But the important part here is that you find that ICR, and then you're able to find that the omega AB is going to be in that direction. And then because of that, we're able to find that the velocity at B is going to be in this direction. All right, so as soon as you know this dimension right here, you're able to get the magnitude of that omega, and then with that, and now we know this dimension right here, you take this dimension and you multiply that omega and you get VB. That's the solution strategy. And if you really wanted to care about that, that's 4.39 is the answer right there. So I welcome you to work that out on your own. And the full answer here says that's 30 degrees down. All right, so another video behind us. Let's never speak of this again. No, that's not how to do it. I'm gonna stop it this way. And oh, it's